All right, so that wraps up inference for regression. Now, when we started this chapter, I promised you that we'd also be looking at how do we deal with problems that are not linear. Remember that this whole regression process is based off of the idea of linear regression, meaning the data needs to be linear. If the data is not linear, then we can't do linear regression. So what we're going to be doing is transforming to achieve linearity. We're going to be transforming the data so that it turns into data that is linear. The rest of the process is exactly the same as what we have done in linear regression back in Unit 3. First, we're going to convert the data to linear. We're going to perform linear regression on the transformed data, and then we're going to convert it back to whichever model it is that we want. Okay? So let's take a look at how we might do that with one of these problems. Imagine that you've been put in charge of organizing a fish tournament in which prizes will be given to the heaviest fish. You know that many of the fish caught during the tournament will be measured and released. You are also aware that using delicate scales to try away a fish that's flopping around and while you're rocking back and forth on a boat may not give us the most accurate answers. It would be much easier to measure the length of the fish on the boat. What you need is a way to convert the length to the weight. You contact a nearby marine research laboratory and it provides a reference data on the length in centimeters and the weight in grams for the fish. Here's a scatter plot of the data. Note that this scatter plot is clearly curved. That data is not linear. Linear regression then probably is not going to be a very good way to go about it. Because length is one-dimensional, weight we can think of as volume. So weight is three-dimensional. Okay, we're going to look at a power model. We're going to see if we can find a curve that fits this data set. In order to do that, we're going to need to transform this curve data so that it looks roughly linear. What we're going to do is take the cubed root of the weight. So of the response variable weight, we're going to take the cubed root of the response variable of weight. Okay, so, or we could cube the length, either way. So what do we have here? Y hat is what we're trying to use to predict, okay? Y hat is going to equal some constant A times the length cubed. But really, what is the response variable Y hat for this problem? That response variable Y hat is really the weight. So the weight is equal to some constant A times the length cubed. So what we're going to do to graph this data set, we're going to come up with what we're going to call a power model. So because this data is not linear, we're going to try to achieve linearity, or we're going to transform to get this linearity. Okay? And how are we going to go about doing that? Here's a scatter plot of the weight of the fish against the cube of its length. So this formula we have down here is what's been used. This formula down here is what we've used to get this model up here. Now, this data does appear to be roughly linear. It actually looks really good linear. So now we're going to perform linear regression on that set, okay, of data. And this is the computer printout that we get from it. Now, how would we go about converting that back? Okay. So part A says, give the equation of the least square regression line. So this is this actual line. What is the equation of this line? Well, the predicted weight, put the little hat on it to make sure that we're representing that it's a prediction. The predicted weight equals the intercept, 4.066, plus the slope, 0.04167, times the length But that's not really the length we use to achieve this. It's the length cubed. So part B asks us, suppose a contest in the fishing tournament catches the Atlantic Ocean rockfish that's 36 centimeters long. Use the model from part A to predict its weight. So if it came up with a 36 centimeter, how much do we think it would weigh? Well, let's plug it in. So the weight would equal 4.066 plus 0.01467 times the length, which is 36 cubed. So I take 36 times 36 times 36, multiply that number by the 0.01467, the slope, to get my prediction. So I would predict that this fish would weigh 688.9 grams. Excuse me. If you look at the model, at the data set we have over here, well, that appears that that's probably relatively correct. We see that the fish that we caught at 36.4 weighed 719. Well, this fish is a little bit shorter and weighs a little bit less. So yeah, this seems to be a reasonable prediction based off of the observed data that we have over here. So we can transform the data by using square root or cubed root or squaring or cubing based off of the relationship between the two variables. Okay. So once again, here is the data set, okay? Shows the relationship between the length and the weight is roughly linear, but not the length and the weight. Remember, we said the weight and the cube of the length, or the length and the cubed root of the weight. Either way, we're going to get the same information. So you could look at it from one direction or the other. That's what this problem is showing us here. That's how we would deal with power regression. If the relationship is cubed, then we cube root. If the relationship is squared, then we square root. But what if the relationship is neither of those two? Excuse me. What if the relationship is logarithmic or exponential? Okay? This is probably the type of problem they're going to expect us to do on the AP test, is convert something that is exponential into linear and perform that process. So how do we know if the data is truly exponential or not? Now, there's something called a ratio test, okay, in which we take each one of these y values and divide it by the previous y value, and then divide it, and then divide it, and then divide them, and then divide them all the way up until we've done that for every one. If all of these ratios are approximately the same, then the data is approximately exponential. Okay, exponential growth. You can look at the graph. This graph appears to be an exponential graph. Okay? It doesn't appear to be quadratic or linear. It appears to be exponential. So what's the inverse operation of raising something to a power? That's taking the log. So what we're going to do is, in this problem, we're going to try to use the year to predict the processing power of the transistor. Oh, I lied. It's not the processing power. It's the number of transistors that are used in the microprocessors. So if we know what year it is, can we predict the number of transistors for the Intel microprocessors? This data is clearly not linear. So somehow I need to convert this response variable so that it does turn linear. So what we did was we took the response variable y, in this case the number of transistors, and we took the log of y. So this graph underneath here is the log of y and the years. So now I can perform linear regression on the log of y versus years, because this data does appear to be roughly linear. So here is a scatter plot of that. Based on the graph, explain why it'd be reasonable to use an exponential model. Well, because the inverse operation of raising something to a power would be taking its log. Right? So, I'm sorry, raising something to the power of x would be the log of that. Okay, so this scatter plot appears to be roughly linear. Part B, here is some computer output from a linear regression analysis of the transformed data. Give the equation of the least square line. Be sure to define any variables that you use. So the log of y hat, or the log of the transistors, is equal to 7.2272 plus 0.3542 times years, or x. So you can think of log of y hat as the log of the transistors. Why do we put a hat over it? To tell us that it's a prediction. So that would be the problem. Now, how would I make a prediction? Well, plug that in here and then do 10 to the power of that answer. So y is going to equal 10 to the power of 7.2727 plus 0.3542 times, we're trying to predict in 2020. Well, in 2020, that's how many years since 1970? That's 50 years. So you plug that in and you'll get an answer of 68 billion. So what we're trying to do is take something that is clearly curved, transform it into linear, and then transform it back into a curve to help us make predictions.